Welcome to the next screencast, which concerns measuring biodiversity, particularly species biodiversity we're interested in here. So the last slide looked at what biodiversity meant and the three levels that we can use to explain biodiversity: genetic, habitat and species. It also looked at the way in which we can assess aspects of biodiversity like populations through sampling. Okay, this looks at how we can measure various aspects of species diversity to give us a picture of what is happening in a particular ecosystem. Okay, so the first slide looks at two ideas: species richness and species evenness in a particular habitat. Let's deal with species richness first of all. This refers to the number of species found in a habitat. Okay, so you need to remember that, just the number of different species in a habitat. Okay, the more species present, the higher the species richness. Okay, so I've got an example down here. Okay, so the species richness of this particular habitat is 2, okay, because we've only got 2 species there. So species evenness is the next value you've got to be aware of and understand what this means. And this is the relative abundance of individuals in each species. Okay, if all species have equal populations, then there is a high species evenness. Okay, so it's relative abundance of each of the number of individuals or the populations of each species. Okay, so to illustrate, if we compare these two situations, okay, so we've got 2 ecosystems, okay, or 2 habitats, both of which contain 2 species. Okay, so the species richness is the same in both this habitat and that habitat. In fact, let's just label these habitats. Let's say this is habitat A and habitat B. Okay, so we have a species richness in both A and B of 2, okay, because we've got the same number of species in both habitats. But if you look at the distribution, the relative abundance, okay, in the 2 habitats, we get quite different pictures. Okay, so there's 28 of species 1 in habitat A and only 2 of species 2. Okay, whereas there's 15 of each in habitat B. Okay, so what we would say is that this habitat B has a much greater species evenness. Okay, and this has got a less species evenness. Okay, so those are 2 key ideas: species richness, number of species; species evenness is relative abundance of individuals in each species. Okay, so you need to learn those 2 definitions. Okay, moving on to another way of representing the amount of species or species biodiversity is slightly more complicated. This one, it's the idea of something called Simpson's Index of Diversity. Okay, so you actually need to remember this. There's a formula here, and I'm going to explain how this formula works in a second. Okay, so the index of diversity, what this does, it's a way of describing a community in terms of number of species and the number of organisms present. Okay, so what it does is it represents species richness and species evenness, and it gives us a value which gives us an indication of the number of species and the number of organisms present in a particular habitat. Okay, and here it says an index of diversity is used as a measure of the range and numbers of species in an area. It usually takes into account the number of species present and the number of individuals of each species. Okay, and it can be calculated by the following formula. Okay, So D is index of diversity is 1 minus brackets the sum of little n over big N squared, end of bracket. Okay, and I'll explain all this in a second, but the key thing is N is the total number of organisms of all species in the area, and D is the value index of diversity. Little n is the number of organisms of each species in the area, and that squiggly line there, okay, or there, which I've had to draw in because it didn't come out when I transferred my PowerPoint presentation onto this particular screencast, but I know I've drawn it in there, it means sum of. Okay, and I'll explain what all that means now. If we went back to my original two habitats, habitats A and B, that we had on the previous slide, what I had was habitat species 1 had in habitat A had 28, and species 2 had 2, whereas in habitat B, remember from the last slide, we had 15 and 15. Okay, so the total, okay, in each habitat was 30. Okay, now what I'm going to do is I'm going to show you how we can work the Simpson's index of diversity for both my habitats, habitat A and habitat B. Okay, so dealing with habitat A first of all, okay, what the formula is this: D equals 1 minus the sum of little n, which is the number of individuals in each species, okay, over big N, which is the number of individuals in all the species, okay, squared. Okay, so to work that out, so I'm going to work this out for habitat A first of all. Okay, so what I'm going to do, okay, is to work out little n over big N. Okay, and I have to work that out for both species. Okay, so that is for the first species, species 1, it is 28 over 30 squared. Okay, so that's done that for species 1, and then it's the sum of, so I do exactly the same for species 2, okay, which is going to be plus 2 over 30 squared. Okay, now if I put all those into the calculator, that's going to give me A equals 0.871 plus 0.004, okay, which is going to give me 0.876. Okay, so that gives me 0.0876, okay, as that value for the first one, okay, and then what I do is 1 minus that, okay, so D for A is 1 minus 0.876, which equals 0.124. Okay, so now I've worked out the value Simpson's index of diversity, which is 0.124. Okay, and I'll come back So the significance of that value. Okay, but what I'm going to do now is to go on to work out do exactly the same, but for my population in my habitat B, my populations in habitat B. Okay, so it's exactly the same formula, obviously, which is D equals 1 minus bracket the sum of bracket little n, which is the population of each individual species, over big N, which is the total number of all species, okay, squared. Okay, so for population B, the first thing again I do is to work out this n over little n over big N squared for each of my species, okay, which is, well, it's 15 of each, species 1 and species 2, so it's 15, the total number of big N, which is the total number of all organisms of all species, which is 30, squared, plus, and obviously it's 15 over 30 squared, okay, and if you add all that up together, okay, so obviously these are halves, okay, and a half squared is 0.25, and 0.25 plus 0.25 is going to give you a value of 0.5, okay, and obviously then what we have to do is 1 minus that, which is obviously a fairly easy calculation. 1 minus 0.5 equals 0.5. Okay, so what I'm going to do now is I'm going to shrink those down so you can see the whole. So you can see my calculations for the whole lot there. Okay, so okay, here's my species 1 and species 2, okay, for habitat A, okay, and I've worked out the Simpson's index of diversity for habitat A, okay, 28, okay, which is little n, the number of population of species A in habitat A is 28, over the total number of all individuals in all species, okay, which in this case is 30, 28 plus 2 is 30, so 28 over 30, square that, plus 2, okay, little n for species 2 over big N, which is 30 again, okay, squared. Add all that up, and you get a value of 0.876, but it's 1 minus that, and that gives us a value of 0.124, okay? And then what we've done is we've done exactly the same for population B, which is 15 over 30 squared plus 15 over 30 squared, which is 0.5, and 1 minus 0.5 is 0.5. Okay, so we've got two values. Okay, Simpson's index of diversity for habitat A and habitat B. Okay, and notice that this habitat has a much lower index of diversity than this habitat. Okay, and that's significant, as I'll explain on the next slide. Okay, so hopefully that gives you a very simple example, and obviously more often we have lots of species, so we might have 10 species, so you have to do those calculations. It will be 10 of these which you have to add up all together to get this value, which you then do the 1 minus of that value. Okay, so what I'll do is I'll give you a couple of examples to do in class of those, so you can work those out for yourself, but hopefully that is a very simple explanation of that. The key thing is this little squiggly line here means the sum of. Okay, so you have to work out little n over big N squared, okay, and then you work that out for all the species present, little n over big N squared, for all the species present, and then you add all those values together. Okay, so that's how that works. Okay, so going back to a summary. Okay, so diversity is a way of describing a community in terms of the number of species, okay, and the number of organisms present. Okay, so it gives us an indication of species richness, which is number of species, and species evenness, okay, the number of organisms present in each species. Okay, so that's what we're looking at here. The next slide talks about the implications of the value you get for Simpson's index of diversity. So let's have a look at the next slide. Okay, so this slide here, as I said on the previous slide, outline the significance of both high and low values of Simpson's of index of diversity. Okay, so again, if we can look at our previous, if we look at the previous values that we had remember we had habitat A had a value of about 0.12, okay, whereas habitat B had a value of 0.5. Okay, so i.e. habitat B had a higher index of diversity than habitat A. Okay, if you remember, habitat A was the one that had 28 of one species and 2 of the other, whereas habitat B is the one that had 15 of each. Okay, so if I look at the low index of diversity, which would, in my very simple example, would be represented by habitat A, okay, this is often due to an extreme environment, okay, where populations are limited by extreme abiotic factors. So there's very few species. Okay, we had the same number of species, a low number of species in both A and B. Okay, so there's fewer food chains or simple food webs and few producers. Okay, it's also unstable, as a change in one population results in changes in all the other species. Okay, so that's indicated by a low index of diversity. Okay, the lowest index of diversity you can get is 0, and the highest index of diversity you can get is 1. Okay, so that's so extreme extreme environments. Okay, limited by abiotic factors. Okay, so that's some sort of physical factor. So it might be you've got extreme, so very high salinity, or the Antarctic very, very cold, or whatever. Okay, so an extreme abiotic factor. Therefore, very few species have adaptations for the survival. Okay, so if you look at sand dune succession, those few organisms that have the xerophytic adaptations to live on the strand line. Okay, to be able to cope with the high salinity and the lack of water. So that would be an extreme abiotic environment. Therefore, very few organisms can survive there. Okay, because there are fewer species, there's going to be fewer food chains, or the food webs would be very simple. Okay, as there aren't very many producers, and it's a very unstable, stable ecosystem. Okay, as if there's a change in one species, that's going to result in a dramatic change in all other species. Okay. So moving on to high index diversity, which in my silly little example will be represented by this, which has got a higher index of diversity. It's still not very high, because actually the species richness is very low in both my examples, i.e. only 2 species. Okay, so it's still not a particularly high. Okay, but higher index of diversities, okay, we tend to find that there is a less hostile environment. Okay, and therefore abiotic environment factors are less extreme. Therefore, more species have adaptations for survival. Okay, more species can survive in the less extreme abiotic environments. Okay, which results in more species, there's more food chains and more complex food webs, and that creates a stable ecosystem. Okay, so fluctuation in population of one species means there's alternative food sources. So a more stable ecosystem for a high index of diversity, and a less stable ecosystem for a low index of diversity. Okay, so those are all the issues to do with Simpson's index of diversity. This last slide on biodiversity looks at current estimates of biodiversity, okay, and discuss current estimates of global diversity. And very quickly we see that there is a huge discrepancy in estimates of global diversity, and I suppose the discussion aspect of this is to try and discuss why there are such discrepancies. Okay, so global diversity would be an estimate of the total number of species on the Earth, okay, which is obviously a huge undertaking to try and work out the global diversity on the Earth, okay, for all sorts of reasons. We reckon there are between 1.5 and 1.67 known named species on the planet Earth, but we know that there are unnamed species, which either are species which haven't yet been named or not even yet discovered. Okay, and this would certainly be true for various types of insects and bacteria and microorganisms that we still we've not yet discovered, and we also have not been able to give one of those Latin binomials to. So scientists have made this estimate that between 5 and 100 million, which is obviously a huge discrepancy between 5 and 100 million. And why is there such a discrepancy? Why do scientists come to such varying estimates of global biodiversity? Is that, of course, different scientists might have different techniques for estimating biodiversity. Okay, so for example, if we worked out the estimate of biodiversity in the county of Wiltshire, okay, and multiply that up to even the biodiversity across Great Britain, okay, we couldn't assume that the biodiversity across Great Britain was representative of what we find in Wiltshire. Okay, so if you obviously multiply that up across the world, we're going to have different amounts of biodiversity in different parts of the world. So you might expect the biodiversity in the Amazon rainforest to be very different from that in the Antarctic, for obvious reasons. Okay, so normal estimation processes are fairly redundant. Okay, also it's very difficult to estimate smaller organisms, bacteria and insects, of what the potential diversity out there might be. Again, because it's a very uneven distribution of such small organisms in different environments, in different habitats. Okay, so again, very difficult to estimate. Okay, and as I've already said, diversity varies across the globe. My example of the Amazon rainforest and Antarctic being two extremes, we'd expect completely different biodiversities in each of those environments. Okay, and again, we've got new species being discovered all the time. Okay, and there's also new species being formed all the time. Okay, speciation, which we talked about before, and there's also extinction happening. Okay, so organisms are becoming extinct all the time. The habitat destruction of the Amazon wreaks havoc on the populations of various organisms, and we reckon extinctions are happening almost on a daily basis to species where habitat destruction is happening. Okay, there's also the other thing that we need to consider in this discussion about estimates of global biodiversity is the effect of climate change on global biodiversity, and I've scribbled down, I'm sorry about my poor handwriting, but I've scribbled down a few ideas here. Okay, and so climate change and global biodiversity. So the idea is that increasing carbon dioxide and other greenhouse gases are resulting in temperature increases, and that leads to climate change. Okay, one example might be changing rainfall patterns. Okay, particularly apposite for our own experience this winter, which a lot of people put down to climate change. I suspect it's got nothing to do with climate change, but the amount of rainfall we've had in southern England in this year seems ridiculously large for what we're used to. And as I say, some scientists have tried to suggest this is due to climate change. But anyway, there is a general accepted belief that carbon dioxide increases and other greenhouse gases are leading to temperature increases across the planet, and that cause changes in weather patterns, which changes in climate, the obvious one being rainfall. Okay, so if you change climate, that changes the environment for organisms, okay, be they plants, animals, or whatever. So this changing environment will have a change, could result in changes in biodiversity. So climate change is an abiotic factor, okay, and as a result species find themselves being poorly adapted to the new environment, okay, because of the climate change, and this will have an impact on biodiversity. Okay, it could be either a positive, increased biodiversity, or decreased biodiversity. Okay, so increased temperature and increased rainfall could increase the growth of producers in a particular environment, which could result in more habitats, which could result in more primary consumers, etc. So it could increase biodiversity, whereas in other situations it could decrease biodiversity. If there was less rainfall, less growth of producers, that would cause less food in food webs, which could reduce biodiversity. Okay, so those two opposing scenarios could happen. Impact on agriculture. Okay, the traditional pattern of agriculture could change because rainfall, which is a huge influence in agriculture, would influence crop growth. So different crops would grow in different areas. Okay, so crops that, for example, need lots of rainfall, cotton, for example, needs a huge amount of rainfall. If the rainfall stopped in areas which grew cotton, you'd have to grow something else there. Similarly, particularly arid climates, there might be more rainfall, and we might be able to grow crops that we could never consider growing in desert regions because of increased rainfall. Again, so the impact could go both ways. Okay, and similarly, lastly here we've got looking at spread of disease. So disease could become more widespread. We know about the female Anopheles, which is a vector for the Plasmodium protozoan, which causes malaria. So if Anopheles became more widespread across the planet, you'd get more malaria. So you might get malaria moving into European countries as opposed to just sub-Saharan Africa, and causing huge problems to our human populations. Okay, and it's not just human diseases. One of the biggest impacts could happen is more widespread plant pathogens. Okay, if pathogens that attack plants started to be, because of climate, started to be able to infect other plants in different parts of the world, okay, that could have a huge impact on producers, i.e. the plants, and therefore the subsequent food chains, and that would link back to agricultural as well. It's possible that we could be affected by all sorts of diseases which we haven't been affected by because of the temperate climate that we enjoy in this country. Okay, so that looks at discussion issues relating to estimates of global biodiversity, but also looks at the potential of changing climate on global diversity, i.e. global diversity could be changing due to man's impact on the environment.